So if you want to do the recording, I'm going to share my screen.
I read an article saying that they're no longer recording in HD on Zoom now because of some bandwidth limitation for all of the COVID stuff. So we'll see how the recording turns out. Hopefully it's still fine.
Hopefully it didn't just record his Gmail inbox.
All right, are we recording? Oh, there's the dot.
Yeah.
All right,
Yeah, we are.
cool. All right, everybody see my screen? Okay, so so I'm going to do a recap on chapters 1 through 8, try to level set for everyone. The notes for the individual chapters are obviously more detailed than what I'm going to cover here. And also the videos of our previous sessions are available. So my intent is to move fairly quickly. Feel free to ask questions, and depending on the material, we'll try and answer everything here. But one possibility is we may set up time maybe at the beginning. We can either do stuff like throughout the week, or maybe even at the beginning of next week's session. We'll have breakouts, and then we can even handle some questions about the first part of the book in the first 15-20 minutes before we start on the chapter. So we'll just see how that goes. So to recap, we've been reading chapters 1 through 8. In chapter 1, just an introduction of the PyTorch library, and basically it's fast. It has a lot of other functionality in terms of being able to work well with GPUs, things like that. And in chapter 2, they introduce some pre-trained networks just to give examples of things that you can do with deep learning. So it was fun to see, the GAN that turned the horses into zebras and things like that. So chapter 3 is where we started going through the actual PyTorch library. And so we introduced tensors, and tensors are basically multi-dimensional arrays. So in other languages, you might be used to a one-dimensional array being a vector, a two-dimensional array either being called an array or a matrix, but it generalizes. And so it's pretty common to have a three-dimensional array. You can think of an image that has height and width, but also different color channels as three-dimensional. If you have a batch of 16 of those images, now basically you have a four-dimensional object. And so in PyTorch, our tensors are just going to be numbers, typically float 32s, and they're going to have a certain number of dimensions, and internally it's going to get stored in memory. It's compatible with NumPy, and not everything you do is going to require it to copy. So the good news is that PyTorch is kind of smart, and it has some indirection, and so it could. So if you, for example, transpose a matrix, it can basically in the metadata talk about how to walk through the data, and it doesn't actually need to recopy all the information just because you transposed it. So a handful of functions that we're going to see over and over again in the code. Not every single function you see, is defined. Every now and then I had to go just online to pytorch.org and just, do a search. Hey, what is this function exactly? But ones that we're going to see all the time, we're going to see squeeze and unsqueeze. So squeeze removes the dimensions. So if you have a three-dimensional array of numbers, it'll turn it into a two-dimensional array of numbers. And typically the dimension you're eliminating is already a 1. So you're not actually changing anything in the data, you're just changing the way you think about it. And so very often we're going to see unsqueeze, the opposite, where we're basically adding a new dimension. So if I have a image and it's 32 by 32 by 3 channels, and I want a batch of images, but the batch only has one image, then I can unsqueeze it and it'll basically add another dimension. So if I put batch at the beginning, it'll be 1 by either 32, 32 by 3, or 1 by 3 by 32 by 32 is the PyTorch convention. So you're going to see squeeze and particularly unsqueeze an awful lot in the code. And then also view, I didn't put it in the notes here, but view is sort of like reshape. It allows you to have different things with, again, generally speaking, when you use view, you're not actually recopying the physical numbers. You're just changing the metadata about how it should walk through the data elements in order to interpret that data. Okay, in chapter 4, there was some other information. We talked a little bit about tabular data, having to encode things. So many of you have probably seen things like one-hot encoding before in other discussions. This book is primarily focused on images, and so one of the key things is to note that images, the standard convention in PyTorch is when you have when you have 3 dimensions, its channels comes first, not last. So channels by height by width, not height by width by channels. And after that, in chapter 5, that's where we got into gradient descent and the mechanics of learning. So here's where we're really starting our journey on deep learning. So there's this wonderful example of Kepler taking a bunch of data, separating it into training and validation, and trying to figure out what's a model that actually approximates this observational data they have for the motion of the planets. And ultimately, they talk about if you have parameters to some unknown model and you're just trying to estimate what are the values of those parameters in order to make this whole thing work, then learning is just parameter estimation. And so these parameters, we call them weights, and we're going to ultimately see if we can find out good values for these weights. And so what we have to do is we have to measure the error between the actual values, so this is supervised learning, the actual values and what our predictions are, and we're able to use basically the difference between those two, the derivative of our function as a gradient. And so what we do is we're going to walk downhill on that gradient. We're going to follow gradient descent. So this means we need a loss function. So this is a function that tells us how far away are we from correct predictions. Lower numbers is good, 0 would be perfect. And so what we're doing with gradient descent is we're trying to decrease that. We're trying to walk it towards 0. And for those familiar with gradient descent, we will get to a minimum, but that may be a local minimum, where there's no guarantee that this is the global minimum, the perfect optimum for this problem. And in general, in deep learning, there's no guarantees you're not going to be at the global minimum, but you'd like to be at a very good local minimum. And so again, there are terms that we expect to see and hear about and talk about. And so one of them is the learning rate. So this talks about whether we're taking big or small. So what is the size of the steps that we take with each iteration walking down? And also the term that you will hear is backpropagation. Is this the name of the algorithm for gradient descent? So backpropagation is how we take the gradient of the functions that are used to calculate our prediction. So then we take the derivative on whatever math we did to calculate the prediction. We take the derivative and we walk backwards and we tweak the parameters that we used in whatever that math was a little bit in the direction that we hope will actually lower our loss. One other thing that we're introduced here is the PyTorch Autograd function. So thankfully, even though the book describes this, you actually don't need to know anything about derivatives or calculus in order to use PyTorch. The library has an Autograd function that automatically calculates the derivatives. And it's actually pretty amazing, like how little code, we'll see in just a moment, but how little code you need. There's so much of it that's just completely built in. So it's really awesome that PyTorch has all that baked in so that you don't really need to worry about that. There's a few notes that were also introduced. One is that sometimes you're doing some calculation. Maybe you're calculating a loss function or some other thing, you're calculating accuracy, and you don't want that to be part of the learning. And so normally this is hidden away in some optimizer function or whatever, but they want to cover it in case you're on Kaggle and you're reading somebody else's code and you see this, you understand what's going on here. So if you have code, you can specify in a block, hey, don't do any gradient calculations on this block. And if you have an entire tensor where you say, hey, I'm never going to actually do any learning on this tensor, it's just there to hold numbers. Maybe it's, you're going to multiply against it. You're going to do some transform with it. Then you can say requires grad equals false. If you do that, then it's a slight optimization. PyTorch knows, oh, okay, then I don't ever need to keep track of what math you're doing on it because you're never going to actually tell me that you want to do backpropagation. How we actually do the backpropagation is we're going to call this grad zero function, which basically sets the I don't know, the hidden variables that hold the derivative, the gradient information, to 0, and then you call backward. And the backward function is what actually calculates all the gradients and accumulates in there. In theory, depending on how you're doing things, you can call backward multiple times. So you could, if you had a batch of 16, you could theoretically loop through all 16, call backward 16 times, and only update your weights once after all 16 backward calls. Okay. And what PyTorch is going to do behind the scenes is every time you do backwards, it's going to just accumulate. It's going to add the values that it calculates in there, and it'll just keep accumulating in there until you call the 0 function. And that's the way things work. So we'll get to the code in just a second. And then ultimately, PyTorch has optimizers, and so the optimizers keep track of the steps that you're taking. So instead of a fixed learning rate, there's different algorithms, there's momentum, there's whatnot. And so actually the stuff that I've just been talking about in terms of dealing with which things you calculate gradients, you don't, zeroing it, whatnot, most of that stuff is taken care of for you inside the optimizer. So if you, especially if you're using one of the canned optimizers, you take that optimizer and you call this step function, and it'll simply update the weights and do all that work for you. All right, so that was a lot of building blocks going up through gradient descent. Let me just pause for a moment here and just check and see if there's any questions, anything I went too fast on, anything I misspoke. All right, so in the book they defined the idea that, you know, we were going to have some sample problem, we're going to have the true values, we're going to do our predictions, and so we're going to have a training loop where we try and identify the parameters. So what it's going to look like, and so what we have to do is we have to initialize our parameters. That's one of the things that we need to do. Okay, we're going to set our learning rate. We're going to choose an optimizer. And then we'll define the training loop in a minute, but basically the training loop is going to say, how long do we go? It's going to pass in the optimizer, the parameters, and then these two tensors right here, these tensors are the inputs for our problem. So when we start out, we're going to evolve this training loop a little bit, but here's our initial training loop. So the training loop is going to say we're going to loop over for as many epochs as we were told to do. And in each epoch, what we're going to do is we're going to call our model, and this can be whatever. So this, when we started out, this was just sort of a very simple linear thing, but eventually we can get to neural networks, convolutional networks, whatnot. But we're just going to call whatever our model is to make basically a prediction. And so this underscore P, this is where they're holding the prediction. So they call the model on the inputs and they get their prediction. So what they do then is you calculate the loss given the predictions and the actuals. And so then you see here what we do is these three things that we're always going to be doing in our training loop. We do a 0, so we start from 0. We call backward, which calculates the gradients, and then we tell the optimizer to take a step. And so this is going to update the weights. And then finally, we just have some sort of print function that says, hey, every so often, print how we're doing. So this is our initial training loop that we saw on the book, first pass of it, and we're going to add a few things to it. Any comments? Any questions?
Is the epoch, is that just your your training data?
Yeah, so typically one epoch, I mean, it can get more complex when you're like sampling the data and you have a really large set, whatever, but traditionally it's just one full pass through your training data.
I see. And then, so wait, the zero grad, just what is the zero grad? Or what does that function do?
Yes, so the backward function has basically a hidden variable inside where it's storing the value from the gradients. Okay. But whenever you call backward, it doesn't actually write the value of the gradients in there. It adds it to whatever was already there. So like,
Oh, I see.
I think about those old-fashioned calculators where it would have like the memory plus button.
Yeah,
And so whatever's in the memory, it's just going to add the current value
I
on your
see.
screen to the memory, right?
So that's why you have to zero all the gradients so that
Yes.
it adds it in. And then the step, what does the step function do? Does that?
So the step is where you update your weights.
Oh,
Okay.
I see. So it actually, so the backward finds the optimal weights for this piece of data, right?
Backwards
then-
finds the gradients, which tells you
okay.
which direction you want to tweak your weights, and the optimizer
Oh,
decides how
okay.
much to tweak in that direction.
Okay, that makes sense. Okay. Thank you.
Yeah. No, that's great. That's a great question. So this is really key. This is what you're going to see in every PyTorch training loop, and Ryan has shared in previous week that once you see
recorded? Sorry.
Yeah, it
Ryan,
is.
is it working? Yeah.
Oh, sorry.
So Ryan has shared that once you see a full productionized training loop, basically you don't really need to necessarily to learn and memorize this anymore, because most people, they'll just like copy and paste that training loop into every project that they use. But this is just us going through and understanding what's in here.
I see.
Quick question. Could you put the optimizer.zeroGrad step in the end? So you call log, then you
You're
take
talking
the
about this step
Zero.
here.
Yeah.
In this very simple training loop, if I had moved this down here, okay, it would work, I believe, because nothing else is touching the parameters tensor, and therefore it wouldn't get confused. Nothing else. But what PyTorch is doing behind the scenes is anytime you do math using the parameters, it's keeping track of that. And when you call backwards, it's figuring out what is the slope of everything that you did using those parameters. Okay. So if for some reason you did something else with the parameters, I don't even know, but hypothetically, if you just had a visualization, if you had some other metric that you were calculating, if you weren't really careful, then PyTorch would say, oh, there's more math you did in these parameters. I'm going to calculate the gradient on all that other stuff too, because it doesn't really know what is part of your neural network and what isn't. It just, if it sees any math using the parameters, it's going to calculate a gradient. It's going to keep track of all that, okay? So basically, as your code runs, it's building a graph of every operation you've ever done using those parameters. And when you call backwards, it calculates the gradient on everything that you've ever done. So in my opinion, it's safest if you call 0 immediately before backward. Then even if by mistake you do something else, it won't get picked up there. I don't know if anybody has any other comments. You can get into weirder, complex situations, like maybe in a GAN or something like that, where you've got two different sets of parameters and you've got alternating training times, and then you got to be kind of like more careful. But in this simple kind of loop, I don't think it actually really matters, because there's only one backward call. So there's really only one time when you need to worry about what's happening.
I have a question. What's the point, like why does the backward function add it to the gradient memory? Is there like a use for that, or is there like a case?
There are uses. So in TensorFlow, you don't have to zero out your gradients. It's automatically done. They actually have a function where, I can't remember what it is. It's tf dot something, where you can just store accumulated gradients. And I've seen cases where they use like both. They zero out the gradients before backpropagation, but they also have accumulated gradients throughout the whole training phase.
Okay.
But I haven't personally had any reason to do that. But there are some complicated models I guess you could do if you want gradients through the whole thing. It's kind of just an option.
I see.
Yeah.
Okay.
So I think like it's been standard in Keras and TensorFlow for a while that it's just automatically zeroed. But they have that option as well where you can see the accumulated gradient. I just haven't found a use for it.
See, I can't think of anything off the top of my head, but one of the things that makes PyTorch very useful for like researchers is it gives you pretty fine-tuned control. So you can imagine somebody who's trying to build a new type of, neuron, a new type of whatever. This gives them fine-grained control, and so they can control exactly when it gets 0 to when it's not. And so what will be true is that your PyTorch code will never be the fewest possible lines. It probably won't be as few lines as if you did something in Keras TensorFlow, okay? But if ever you want to do something that Keras won't let you, you're going to be really glad, because in PyTorch, you just have full control. And so that includes here when you call the 0. So if you ever, for some reason, didn't want it to 0 and it automatically did it, you would be really frustrated. So
I see. Yeah.
One little line, and then it's very explicit for you. You know exactly when it's getting zeroed out. Just like I said, in those old calculators, you have memory clear and memory plus.
Yeah.
You're just in full control.
It's kind of interesting. In TensorFlow, it works the other way. It's one simple line and it will show it to you. But I feel like most people, most of the time, they always just end up zeroing the gradient. So I feel like it's one of those options that might not need to be a default, but I haven't looked into it that much. And it's pretty frustrating too when you try to look into why do you have to zero gradients. Everyone just says like, oh, you have to do it because it resets the gradients. Otherwise, it keeps adding them. But I've never found out why they kept it as a default.
It's because you want to give the optimizer the flexibility of doing whatever it wants to. And so if you're able to, some optimizers might prefer to have multiple gradients to choose from and to use in their decision to decide what step to take. It's like when you're walking around and trying to find the valley just by looking at your feet to see what the slope is. You sometimes want to take a few steps and look at in multiple directions and get multiple different slopes before you decide where to go.
Is that different than a cumulative gradient though? Because I understand that with multiple different gradient calculations, but like different optimizers, but I don't see how the cumulative gradient would be that useful.
It's the same as like for a batch size. So it was a long process before they finally figured out that mini batches were good, that they were the best ones. But if you let your optimizer find the right batch size by accumulating the gradient for one sample, then 2 samples, then 3 samples, it can go through during its process. It can be accumulating different gradients across different subsets of your batch. It can decide which of those is best representative, which one of those is too smooth, too averaged, and which one of those is too stochastic, too random.
That's kind of wild. So just imagine that you don't explicitly call 0, you just call optimizer step, and it decides which gradients it's going to use. And if it uses them, it zeros them. But if it doesn't use them, then it just lets them continue to accumulate.
And Torch's default is to give the developers of these algorithms as much flexibility as possible. So they want to make sure that that you have the option of giving those optimizers all the information instead of just one piece of information.
Oh, I see. Okay, that makes sense.
All right. So I am now going to show another version of this training loop, the same one that we just saw. The only difference here is that we're going to have validation data in here. So this means that we're going to be able to calculate metrics on validation, throughout the training. And so the difference here is we have extra parameters we pass in because we need to pass in the validation data and its labels. Okay. We're going to call the validation model on our data so it can make predictions. And we're going to calculate a loss comparing the predictions to the actuals. But one thing you'll notice is this code is identical to before, where we call backward on the train loss, we call a step, and then we do not train on the validation data, right? Because the whole point is it's validation, we're not training on it. So you'll see you do this so you can calculate metrics, but we don't train on it. Otherwise, this code is identical. So in the book, there are some loops that are simplified where they don't have validation, just so the code's a little shorter. But in a production training loop, you're always going to have validation data. So then in chapter 6, the book talks a little bit about actual neural networks. I'm not going to say too much about it, but basically it's loosely, originally the concept came from thinking about real biological neurons, the idea that they require an activation in order to actually fire. And so we can stack these neurons together, and ultimately the math inside of them tends to be linear. And it's this concept of an activation function that turns it from something that's very linear to something that's nonlinear. So some pictures you can see here, the sigmoid function, this S-shaped curve, hyperbolic tangent is a similar S-shaped curve. And then recently, you're going to see a lot of networks that use ReLU. And so this effectively says if it's a negative number, then use 0. If it's a positive number, use the actual number. So effectively, it's calculating the max between 0 and the number itself. And so this is clearly nonlinear. This is much faster to calculate than those S-shaped functions. And so ReLU actually has very nice convergence properties, but one of the other properties it has is it's so much faster to calculate. So it actually helps speed up the iterative process when you're training neural networks. So in PyTorch, we have this NN module. That's the neural network module. And so this is where you're going to have the different layer types, and you will have activation functions and things like that. So if you look at a very simple linear neural network, so before we're getting to anything fancy like recurrent networks or whatnot, sorry, one second. So then you're basically going to have your weights and your bias. And so for those familiar with this, the math is you take your inputs, you multiply by the weight matrix, and you add the bias. And so that's the output of your neuron itself. And then you pass it through typically, again, the activation function. So one thing that's different when we use a predefined type of node, even if it's just a linear node in PyTorch, is that the parameters, in this case, the weights, are part of that class. They're part of that object. So in the previous code, if we went back and looked at it, you would see that the parameters are manually kept separately in a tensor. But now we don't need to do that anymore. So here is some very simple code showing a neural network that can do something interesting. It's going to take its inputs. It's going to have one hidden layer with 13 units. And how we know it has 13 units is because the output is 13 channels. And then finally, it's going to have an output layer that takes those 13 and outputs a single value. So whenever you have a unit, if you know how many outputs the individual unit has, then basically the number of units is going to be this number divided by the number of outputs per unit. So for most units that have only one output, then this is just the number of units in that layer. And I will say that if you watch very closely, you'll hear me talk about layers and units, which for me is the terminology that I'm used to. And in the book and in PyTorch, I think they use modules instead as the standard terminology. So just in case you don't get tripped up on that when you're reading the book. So now that we have this actual layers that are built using PyTorch, neural network NN objects, then our training loop changes ever so slightly. So in this case, we're passing in the model, so our neural network architecture, into our training loop. And in this case, we're also, instead of having just a random defined function, we're passing in what loss function do you want to calculate. And then really the only difference inside here, inside the for loop, is in the previous training loop, you would see where we would pass in the data and the weights. But in this case, we don't need to do that because the weights are built into the model, into the neural network. So where I have highlighted in red, there used to be an extra parameter. But otherwise, switching from handcrafted tensor stuff to using the neural network class, basically not too much change. Our for loop looks pretty much the same, right? And again, this block that we talked about remains unchanged. We call 0, we do backward, we call optimizer step. So there's a bunch of different optimizers you can choose from. You can write your own if you really want to, but you're basically going to do these 3 steps. This is the key part of learning.
What's the difference between what you were showing us just now and what we were doing before? Like
yeah. So before you may not have caught it, but they were building things up and they weren't actually using neurons. They just had handwritten code that said, here's an input. I'm going to multiply it, add a bias, and output it. So it's just a handwritten function. Whereas now we're actually using, in this model, we're using the
a neural network.
Yes, we're using the NN module, and we're using this NN linear, and so we're defining our model. Just so you know, I've copied and pasted code. Not everything quite matches. So here it says the word model, and here I have sequential model. And actually in the book, there's this extra line of code that says model equals sequential model.
Oh, I see.
Okay. So these two don't exactly match, but basically I'm now using the neural network modules, the linear and the hyperbolic tangent modules, instead of my handwritten code with tensors.
I see. So, okay. So like before, what we had was basically some custom function that you could use with specific parameters. And and that's why we had to find the gradient. Okay. I think I understand.
Yes. And I didn't show. So if you go, so these codes are all snippets from the Jupyter notebooks that come with the book. So if you go, you can see the full code, you can run those. What I'm trying to highlight essentially here is primarily some slight evolution in our training loop, because that's really the key thing that we're going to end up with coming out of part one. Is we're going to understand that tensors are multidimensional arrays, and that here's a training loop that will actually learn parameters for us.
I see. And so the nn.linear113, that's the hidden layer, right? And then the one underneath it, not tangent, but the other linear, that's the converting the hidden layer to the output.
Yep, that's our output unit.
How do you say how many inputs you have? Do you have to specify that, or?
So let's see here.
It's the input layer, that first hidden layer that you mentioned, the linear 113, that tells you.
Oh yeah. So this is actually the number of inputs, and you do.
I see.
Explicitly in this, if you go back to the chapter, you'll see that they handcrafted an example where they're basically looking at temperatures on a thermometer.
Oh, okay.
The thermometer's not calibrated, so it has a single number input. When you do real data, if you have 50 columns, that one is going to be a 50. If you have an image, then it might be multi-dimensional. It won't just be a single number. It might be 64, 64, or if it's 3 channels, it'll be 3, 64, 64.
If it's 64 by 64, would you just make it so it's just one giant column of data, or how would that work when you feed that to a neural network?
We'll see that. Typically, you are going to retain the shape.
Okay.
So it'll be 64 by 64. It won't be whatever that math is.
I see. Yeah. Okay. Thank you.
Sure.
I like to explicitly name my parameters for those layers, because some more complicated layers have a lot more parameters than just the inputs and then the outputs. So I actually like to label them by their actual name within the keyword arguments, so I remember which is which.
Yeah, there
makes a big difference, like on CNNs, because you have to know exactly what your input size is so that it matches up with the original image size that you came out with, so that your last layer gets it right, because there's going to be some expansion. Anyway, with CNNs, it's really important to know what your size is.
I see.
Yeah, I think there was a section in chapter 3 that talked about a PyTorch experimental feature where you can name the parameters, but name your dimensions. But even if you don't use that, you can always just have a comment in your code that explicitly says, hey, I've got 5 different dimensions here. Let me be really clear. It's batch. And then it's,
I see. I was just saying, within your code, just keyword argument. Just use the keyword argument name. Instead of using a positional argument, use a named argument. Because the name says input. And says output.
I used to do what Ted is talking about, where I'd have literally hashed out line at the end of every line and say okay, this is the dimensions, it's this by this by this, this layer is this, and I just comment that all out, and I just start doing the keyword arguments. Took me a solid 6 months to switch over and realize those work too. But always having comments really helps too, especially when building your own models from scratch. I really need to focus in on what the dimensions were, and I just write literally in every line what everything is, where it's going, how it's being transformed.
And if you have to have some math, it's really like if you have an image and you want to turn it into a linear layer at the end, So if you it's like, 256 by 512, and you put that in your comment, that's really useful as well.
Oh, I
Yeah.
see. Okay.
Yeah, and in fact, Ryan had it in the notes. I don't remember which chapter it was, if it was 5, 6, or something like that. I didn't include it in the recap, but there's a wonderful comment in the book where the author says basically, hey, just so you know, like really experienced researchers will sometimes write their code and they'll say, okay, so here's this 2D convolution, kernel size 5 by 5, without padding, with a stride of 2, and they'll get the math wrong. And so they're like, even the best of us, sometimes it's just, we have to try it a couple times before PyTorch stops giving us an error that says your tensors don't have the right matching sizes.
I see.
So I thought
Okay.
that was pretty great. All right. I'm sorry, guys. Hold on just 1 second here.
Yeah, I had a similar situation when I'm like using like word embeddings or something, and then you have to like flatten them and just adjust the sizes and stuff, and just conceptually understanding how those word embeddings even are and what the dimensions are. I just make a lot of comments at first to start understanding like what each dimension is and where it's coming from and how it's being transformed. It just helps like mentally understanding what's going on too.
Thanks, Fibu. Okay, so moving along, so chapter 7 introduces a simple problem. Imagine that they have this camera and it's trying to take pictures of birds, but sometimes planes fly by, and we want to build a classifier so that we can automate so that the researcher only has to look at the real birds, they don't have to look at the airplanes. Just a made up little example, but just to get us something a little bit more complex than the initial temperature fake problem. So now in this case, we haven't gotten, the next chapter, we're actually going to get to convolutional neural nets. So in this case, they're just treating, like Matthew was asking, they're just treating all the pixels like one big giant long thing. And so it's 3072 pixels as our input. So we're not actually treating it like a rectangular or square image. We're just treating it as a single pile of pixels. So this is still using the sequential model. If you're familiar with the sequential model in Keras, this is kind of similar, but sequential is not going to get us very far in PyTorch. It's very limited. And then also we see then that loss functions, we don't have to calculate them ourselves. There's a whole set of loss functions already built into PyTorch. So in this case, here is the PyTorch built-in negative log likelihood. So they just abbreviate it, NLL, loss. So if we look at our training loop in chapter 7, the one thing that changed is we are now doing it in batches. So I haven't really gone into it, but they've talked about data sets. They built a loader. And so now this batch is 64 images. So before we had only one for loop. Now we're going to have 2 for loops. The first for loop, again, is for epochs. How many times do we want to go over our entire training set? But in this case, our training set is broken up into chunks of 64. And so we need an inner for loop. Otherwise, the rest of our training loop looks the same. Again, this is simplified. It doesn't have validation. But you basically make your predictions by calling your model. You calculate your loss. And then these famous 3 lines, 0 grad, backwards, step. Okay. One thing that is nice, I mean, a lot of things are very manual in PyTorch. Batch size, you don't need to do calculations yourself. PyTorch pretty much seems to seamlessly handle. So if you change the batch size, you don't have to update your code. You can just change your batch size, and then the rest of the code continues to seem. I don't know if we'll run into a counterexample, but so far what I've seen is you don't have to change your code when you change your batch size. And then the last chapter in part 1 was where we actually introduced convolutions. We introduced CNNs. So I'm not going to take time here to talk about what convolutions are. If there are people who haven't yet looked at convolutions, like I said, you can message on the Slack, you can private message me, and maybe what we can do is we can set up 15 minutes at the beginning of next week to talk about convolutions if anybody wants that. We can do that in a breakout. But convolutions, you're going to take a small window. So you're going to look at the local pixels that are near your pixel of interest. So a 3 by 3 would be looking at the 8 that are immediately surrounding it. A 5 by 5 is a slightly bigger window. And you're just going to slide this over the whole image, every possible location, and you're going to do the calculation by multiplying that small filter against the actual pixel values. And you can do this. We typically talk about 2D images, but you can do it in 1D, 2D, 3D, whatnot. And ultimately, these filters have really interesting properties in terms of being able to say, hey, are there a bunch of pixels, for example, that are turned on in this shape or something like that. So we introduce convolution and then also the idea of pooling. So with the idea of pooling, whether you do max, average, or whatever, these days typically it's going to be max. So if you have 2 by 2 pooling, then basically what you're taking is the output from 4 different convolutions and you're turning it into one result. So ultimately what you're doing is you're shrinking the amount of data, which is one thing, but it also means that everything that you're looking at is now sort of twice as big. And so so pooling is a way of basically in successive layers of your network having a wider view of what you're looking at. So initially you may be looking at a 3 by 3, but then if you do 2 by 2 pooling and then another 3 by 3, instead of that looking at 3 pixels, it's now looking at something akin to, I don't know, 8 pixels across that's its field of view. And if you alternate successfully convolutions and pooling, then the later convolutions, they each have a wider part of the image that ultimately feeds in and affects their values. And so this is how you can detect larger patterns. So if you're trying to detect cats, in the early layers, you may be looking for just lines, or you may be ultimately finding something that looks like an eye, a nose, an ear, but ultimately you need something that's going to look for a face, and it's going to look for, eyes and nose combined and that kind of thing.
Why do you use a pool rather than just a larger convolution?
That's a really good question. In some cases, people do choose to use larger convolutions. So they say, hey, I'm not just going to use 3 by 3s, I'm going to use a 5 by 5 or something like that. Ultimately, I don't know if somebody else has a comment on this, but I would say that you're going to have convergence properties and you're going to have calculation cost issues. So in the extreme, if you had a 256 by 256 image, you could say, why don't I just use a convolution that's 255, right? And so that's going to be ginormously expensive, and ultimately it's not really going to work well. So the smaller convolutions allow you to detect smaller patterns, and there's this property that I didn't really mention, but it is here in the notes, is that there's this idea of translational invariance. So if you're detecting a vertical line with a particular filter, since it's running over the whole image with that convolution, it'll detect a vertical line anywhere. Whereas if you had a giant convolution that was 255 by 255, it wouldn't really generalize. It doesn't have that translational invariance. It's basically just looking for particular values in particular locations. I don't know if anybody else wants to add to that answer.
I think there's kind of a sweet spot you have to find. So you don't want to go too small. Otherwise, you're just kind of looking at every pixel, which you really could do, which is kind of useless. Let's say you have like a convolution of like 4 by 4, then you can actually pick apart little things in those like 4 pixels and see, okay, what relates to what else. If you have something too big, then you don't get enough specific information out of those, So, I mean, you could really just do one block as the whole image. You could split it up into 2, 4, whatever blocks, but you're not going to have enough like useful information out of that. So you want to go, because pooling is kind of separate. Pooling is like, okay, which one of these blocks activates the most? Like, where do I see relevant information? So that's why you can have something like slightly bigger, because it's going to focus in on its own point. So if we think of something like the regular MNIST data set with just like digits. So let's say I have a block that's like a little bit bigger. It'll still be able to realize like, okay, I want this part, like this is the curve of the 9 or whatever. And it'll have those, like that part of the image actually fire up. But if you go too big, then you don't really have any distinction. Like you want to go, yeah, you just kind of want to find that sweet spot. But pooling is a little separate from, like, I wouldn't say you want to justify a smaller or larger convolution size with like more pooling or different types of pooling.
Can you hear me right now?
Yeah.
Yep, we hear you, Maya.
Good. Okay. The convolution filters, they're done by random. And by random, we can, on a small filter, we can find out some lines, some arcs, and such and such. But if you want a big filter which detects a cat's face, it's the probability that you can get it is very slow, and you need a lot of filters just to get something similar by randomly. Sorry. By random.
That's a really
guess.
good point. Thanks. Yes. So they are randomly initialized and they're learned. And so you can imagine, like Maya said, if you had a 3 by 3, there's 9 numbers, you might get something useful with randomly. But if you had my extreme example of 255 by 255 filter to randomly get anything that's even remotely helpful, the odds are infinitesimal. And so I don't think that one would even, in actuality, wouldn't really converge.
Yeah, the
Okay,
cat face is a, sorry, go ahead.
I was just going to move on, Vibhu. So,
Oh.
so here we have a simple mock network that was defined using the sequential model. So there's actually, in the book they note there's an important step missing here. But you can see what they do is they do a 2D convolution, they have an activation function, they do pooling, another 2D convolution, activation, pooling, and now they want to make a prediction. So they actually have a dense linear layer, a hidden layer, an activation, and then an output. And in this case, it's outputting, it has 2 outputs. So the thing that's missing here is related to what was asked before. So the output of this max pooling is going to be a 2-dimensional tensor. And linear requires a 1-dimensional tensor as its input. So in fact, if in the notebook, they literally run this code and you get an error message that says that the output of this tensor, this layer, isn't the right shape for the input of this layer. Now it actually has the same number of floating point numbers in it, but they're in a different shape. But this just shows sort of simplistically how the layers sort of pile up. And so very recently, apparently, they added actually a flattened layer that can do this reshaping for you. But in the original PyTorch, it wasn't there. And so you actually were required to build things by subclassing the NN module class. And generally speaking, I think all the sample code you're going to see, people are doing complex enough stuff, they're going to do it this way. So sequential is great for learning, but you're probably not really going to encounter it in the real world. So then just scrolling down a little bit, what you do in subclassing the NN module class is you have to have just 2 functions. Init is where you define what are your different layers, and in particular, PyTorch needs to know what are all the parameters it has in there. How many of them are there? What size are they? So the equivalent of our sequential thing here, you see we do 1, 2, 3, 4, 5, 6, 7, 8, 9 layers if you're counting, pooling and activation, everything equally. And you can see here, you can just say, same thing here. I want 1, 2, 3, 4, 5, 6, 7, 8, 9 things here. I'm just going to create them. And so in this simplistic code, it very much mirrors what we did in the sequential model, the sequential API. So init just basically creates all these things. And then forward is where you tell it how to do the math. How do you make your prediction? If I give you inputs X, how do you actually make your prediction? What do you do? And so just to save some space, they actually you'll see, they put 3 things on one line. I'm going to do a convolution, then the activation, then the activation, then the pooling. So it's not 9 lines, but you could have written out 9 lines if you really wanted it to just exactly correspond. And so this is sample code that very much mirrors the sequential. And so for learning purposes, it's nice, but actual people don't really bother writing it this way. So there's a functional there's a functional API, and basically the functional API says, hey, you know what? When you're doing max pooling, there's no parameters. There's nothing that needs to be learned, so we don't really need an object. It's just a function call. Hey, when you're doing an activation, it just says, if I have this number, you know, whatever, for sigmoid, you input a 0, I'm going to spit out 0.5 or whatever. I don't have any state. I don't have any parameters to learn. It can just be a function call. So that's what they do here. So they shorten it by not defining 9 things. They only define 4 things here. Your convolutions and your linears actually have parameters, so you have to initialize them. You have to create them. And then down here, you'll see instead of having to then have the full object, there's the torch tan h function, and there's the functional max pool 2D function. These have no parameters, nothing learned. It's just a function call, just like square root. Square root has no parameters. You give it a number, it outputs a number. And so this is typically now what your code is going to look like. It's going to be a little bit shorter, a little bit more compact. And so for anything that doesn't have a parameter, you don't bother creating something in a init. You just deal with it. And so again, the forward is just, what is the math I'm going to do the calculation? When you do the calculation, PyTorch behind the scenes makes a graph of every calculation you've done. Here I added, here I multiplied, here I divided, here I did whatever. And therefore it knows when you call backward, it knows how to calculate what the gradient on that particular calculation was. And so this is now our final training loop. In this one, you will see that the only difference here is that they create this extra variable so that they can accumulate what your loss was over time. And so they can show that for the average loss across the whole epoch. But at this point, our training loop is pretty stable, and this looks very much like what you're going to see. This is still a little bit simplified because you don't have the validation code in here. But otherwise, this is fairly close to what a production training loop is going to look like. And then finally, they talk a little about neural network architecture. So we showed a simple one that only had 2 convolutions. You could go deeper. You could do 3 convolutions. Or you could go wider. So you could stay with 2 convolutions, but in each one, you could have more units. And then there's also a little bit of discussion about, as we go deeper, regularization may be important. We don't want to overfit, and introduces dropout, which is very commonly used these days. Introduces batch norm, which is pretty common. And I will say for me, I still don't feel like I fully understand how batch norm really works during training. I mean, I understand the definition of batch norm, but in terms of like what really happens and the fact that the normalization is changing throughout your different batches and throughout training, like that to me, that's still a little bit black magic. All right, so I'm going to pause here. Any other questions before I turn things over to Ryan? All right. Thanks, everyone. I know that was pretty fast, but I wanted to make sure I didn't, that I left enough time for Ryan here.
Thanks for the recap, Ed.
Yeah, thanks for putting that all together.
I think it was very well.
And just so you guys know, so the notes and the videos from all these sessions, we're just keeping links to all of them on our GitHub repo. So these notes are also available. The link to them is also available on our repo.
We've got Zoom inception for a second there. Okay, so all of that stuff that we just learned about, all of the building blocks, after we have all of that knowledge captured away, now in the second section of the book, what we're looking at is an actual practical application. So trying to put it all together and make something useful with it. And so the one that they've configured here for us to start learning about is detecting malignant tumors in the lungs from chest CT scans. And so in the rest of the chapters of the book, maybe not the rest, but the next few, I haven't looked that far ahead, is we're trying to figure out what is the pipeline to actually prepare something like this. And so just to start off with the understanding, it's CT scans. These are 3D arrays of images. They explained it as basically imagine like stacks of 2D grayscale images. So they've got a depth, which is the like vertical axis potentially, and then you've got the height and width, which is like the physical dimensions of the person inside of the scanner. And so the goal of this is we're trying to detect the tumors. And so the point of these two chapters, chapters 9 and 10, is understanding what is in this data, how do we load it, how do we prepare it to be ready for a neural network. And we come into some pretty real world problems. And so they walk us through that process. And so in the past, we've worked with some pre-built data sets. In this one, we have to do the actual data prep and data loading process in order to get ready for that. And so one of the things they mention is it's pretty important to start with the big problem, which is understanding that we're trying to detect tumors from these images and then break it down into smaller problems. So the first one being, let's load in the data and then go from there, basically. Like I said, stacked grayscale images, it's got depth, height, and width. So typically on an image, we think of the pixel. In 3D, it's called a voxel. That's not really material, but something that you should just be aware of in your vocabulary. And so in the CT scans, what it's actually measuring, they told us it's the average mass density of the voxel. So it's saying specifically at this depth, at this height, at this width point, they've got a certain density, and I can tell you various different things about that specific location in the scan. So in this one, we need a data loader. That's the big thing that we're working on, is we have this pile of data. How do we prep it? And so they kind of show the various different steps of the model that we're going to need. So the first step is going to be loading in the data. The next step they propose is segmenting the images. So we have those 3D boxes. We want to be able to figure out where in that 3D image potentially there are nodules. And so after that, they want to group those together and then pick out the ones that are interesting. And then they want us to be able to take those subgroups from the images and then classify them as nodules or not nodules. And then after that, once we've made those predictions, they want us to aggregate it in some way and make an actual decision with it. So does this person have a tumor or not, basically? And so it's pretty important in here to research the data, and that's going to be consistent with all of your projects, basically. And they go into some depth in the chapter, but I would say the important thing is to kind of just look at their steps and understand the general process, not necessarily the specifics of here's how you load a DICOM file or here's how you load whatever, because you're not always going to be working with DICOM files. You might encounter something else. And so you need to be aware of it. It's just a general process. You need to say, okay, this is the format the data is given to me. I need to figure out how to open this kind of file and manipulate it in a way to make it useful. And so one of the things about this kind of data is, even though we're working with 220 gigabytes, that might not actually be that much in the context of this kind of data. So they said it's about 220 gigabytes once everything's decompressed, but that might only represent 2,000 patients or something like that, because this data format is pretty storage expensive. And so in the past, we've had kind of good luck with CFAR and various different things where you have lots of data available. And so just something to keep in mind. Sometimes data is more valuable and hard to get than others. In this case, it's pretty hard. So everyone is operating on this same Luna data set, and it's big, but it's not necessarily sufficient to solve the problem, but it might be good enough to learn about it and get in the right direction. And so in this Project Luna thing, they have a leaderboard. So if you go to the website, they've got a list of all of the top performers, basically. And they also have the corresponding scientific papers. So if you want to go there and you want to see what is this state of the art on this specific data set, what has the best generalization capability, you can go to the website and you can read through the scientific papers and you can see what seems to work, what seems to not work, what are the various methods that people have already explored. And so that was kind of the gist of Chapter 9, just a high level overview. They had plenty of detail in there, but I don't think that it's really material to generally learning PyTorch. It's just specific to this problem. Did anyone have any questions on Chapter 9?
Did you have, I guess, any recommendations for anyone not with 230 gigs of free space in graphics cards?
So the hard drive spaces, there's not really much way around that. You either have to pay for it on the cloud somewhere or you have to just buy your own. There's no real way around that. They did mention that if you want to, you can just download a chunk of the data. So they have it split into, I think they said like 20 pieces or 50 pieces, and you can just download one batch and then you don't have to do the entire thing at once. But I would say that's not really viable. You kind of have to put the investment into a hard drive, or if you're doing something on the cloud, you have to pay for the storage space.
It's not that viable, but you can run off like one of those little external SSDs. They're not too expensive. Like a terabyte might be like $70 or so. And I don't think they're that slow, but it's an option.
Yeah.
And the code is, or there are a lot of places in the code where it tries to do as much caching as possible with regards to the images and the data. So at any given time, it's going to keep that image in memory and whatnot. So you are going to see some slowdown, but they take great pains to mitigate that.
Mm.
I was kind of thinking of trying to do it through Google Drive, since all the resources are already there on the Colab notebooks. And I mean, I have enough space there, but I was just curious of other people's opinions on that.
Mm.
I've worked with a lot of stuff in what's Apple's storage? iCloud. I've got like, I think a terabyte of iCloud storage. So I think the default MacBook like desktop just saves to iCloud anyway. So I've had a lot of stuff just in my iCloud drive and done that.
But I think in Tommy's scenario, if he's trying to work on Colab and he needs to access it in some way, I think Google Drive is an option. I'm blanking on what the other one is, but if you need something that you can actually like attach to a Google Colab session, I know there's options. I forgot exactly what they were.
I think I've done that through iCloud, because the default Mac desktop, they just have that stored in your iCloud drive, and I've just downloaded data and it just goes to my desktop, which is in iCloud, and I can just upload it just fine on Colab.
But if you'd need 230 gigs associated with a Colab session all at once, you have to have something that is kind of attached. And I know that you can plug in a Google Drive and just have data that's kind of in a connected storage, but I've heard that it's relatively slow. So I don't know what the other way is, but I know that there is one that people have said is much faster. I'd have to look into it. I'm not as familiar with the Google resources.
Okay, that's cool to know.
And
oh, go ahead. Sorry.
I was going to say I would hesitate to do it, but Python does have a lot of nice file readers. So it does have a built-in zip reader. Technically could leave all the data compressed and update, because the next section is all about creating an interface is for reading the data. You could add some zip unwrappers into that part, and
I forgot
again,
Tommy was talking about using cloud services because he doesn't have a GPU, so I don't think that would work. Unless, yeah,
I'm saying because it reduces the overall size that you need for your storage, not for your processing. The processing still full size.
Cool, that makes sense. Oh, sorry, go ahead, Ted.
I was just going to say, I think this is a great question for us to talk about, because this is actually one of my frustration with a lot of the Kaggle competitions. This is just like, it's an enormous amount of data and I can't run it on my local computer. And so sometimes it's frustrating to try and work on these projects. I think it's a real issue.
Yeah, I've done, so for work, that's what I do. I think there's a function that Google built called like G Drive, where you just basically put the command in, then I'll ask you for a code, which you then tie to your Google account. You can access it that way. I don't know about speed problems though. I have heard about that. I haven't experienced it, but I have heard that problem. But I was just, curious in general, because I know a lot of people don't have a graphics card locally that they can use, such as myself. I just have my laptop with an Intel GPU. So yeah, just kind of seeing, I noticed that Kaggle also had, I don't know if they had the total data set for this, but they had something for this Luna data set. So for others as well, maybe that's an option if they can't compute it locally.
Yeah, it's entirely possible they have it on Kaggle. You can upload fairly large data sets to Kaggle. I don't know if they'll allow you to do 230 gigs, but if you make a data set public, the limit is fairly high. I don't remember exactly what it is. But they do also have some data sets they host on their own, and you can just connect that to a Kaggle instance. And I know they have some massive ones like terabyte plus, but I think those are ones that they themselves manage. I'm not sure.
No, I was just thinking in the general context of running through the exercise of this book. I know in the book that they said, oh, we'll just look through the notebook, but it's always helpful to actually run the code and try it against, especially if you have the data set or some way to access that.
Yeah.
If you do plan on working with it long term, if you have a newer laptop that has a Thunderbolt 3 port, they make like GPU enclosures. So I think they're like $150 to $200, and you just plug it into your laptop with that Thunderbolt 3 port, and you can put like a desktop grade graphics card in there. So if you have like one of those Ultrabooks, it's maybe like $400 or so for a pretty solid system. It's a little pricey, but it works.
Are you running on a MacBook, Tommy?
Then it wouldn't work.
Yeah,
I am. Yeah.
Okay.
Well, MacBook Pro, but it's an older one. It's not the doesn't have Thunderbolt.
Yeah. If you're on
The
Mac,
newer Macs have problems with NVIDIA too, though. So
yeah, that's why I was just going with the cloud notebooks. But so just wondering about cloud storage and how to connect that, or if anyone had any other recommendations. But yeah, thank you, everyone. Makes sense.
any other questions?
has anyone found a good way for like setting up their desktop PC and being able to like connect to it from a laptop and do work on it? I was considering like taking a trip for a bit, but I didn't want to bring my whole PC for work. So I didn't know how to like set it up to like run a server and just connect to it other than like Google Remote Desktop, which I've tried, which is a little slow.
I do that. What kind of desktop? I do that for work all the time. They have one of those NVIDIA servers. So I just local it through my web browser, or VPN in and then access it through my web browser. So what's your desktop setup?
I have it running Linux and Windows. I could honestly work on both, but yeah, I've just never like tried how to set it up to be able to connect to it from my laptop. I've just used Google's thing.
I just do a SSH session, use Screen or Tumix and then start a Jupyter notebook within that, and then do an SSH tunnel, using the ports that you need, so you can redirect it and then you can access it that way.
Okay, cool. Doesn't seem that hard to set up.
Yeah, the only thing that you need is that that token that is displayed when you start a Jupyter Notebook. But I mean, it's cached after that, so it doesn't even ask it that often. But it's really simple, and then it's running all the time, and you have all the access.
Oh, awesome.
I'm not sure if you were describing like when setup when you're actually running notebook on the server on Linux, but that's what I would do. I would just connect to it from Linux to remote server on the home Linux session.
Yeah.
Because then you don't need the full session. It just goes through the browser. And you can do the same thing with Python code. I think Adam does that, and I think VS Code also allows you to do that. Basically, you have remote code, but you like edit it locally.
Oh, cool. Cool. Thanks for the advice.
So you guys are all talking about talking about when the notebook and the desktop computer are on the same network, right?
Well, I use a VPN, but it's the same thing. Yeah,
that's
same
what I was thinking.
Local network.
Right.
And VPN bridges that. So
so I was going to ask, is there an easy VPN for home use? If this isn't for me, but I know people talk about so if you're at Starbucks and you actually want to be able to access your home Jupyter server or whatever. I don't know if people have figured out sort of easy home VPN.
So for Linux, there's a ton of free VPN services. Open source, I should say, that you can use to host the VPN on your server to connect. The whole thing is trying to get that address. So the question of do you have a static IP address at home, which usually requires a business account, or is it dynamic? If you have dynamic, you can use a service like Dynamic DNS, which basically looks at your IP address. You run a little service on your computer, constantly looks at your IP address, and then updates a record that they create. And you can pay, and that's a paid for option. It's pretty cheap, I think. So then you can just access that URL that will automatically update the new IP address that you have at home.
There's a service out there called Tailscale, Tailscale. It basically creates a mini overlay network. So it doesn't really, you're not trying, you don't have to manage where am I connecting to or where am I connecting from? It kind of shares all that information via the service. And so you just, whether you're on the road or whether you're local, it still looks like you're hitting the same IPs.
Cool.
Takes a lot of VPN setup out of it. So.
That's exactly what I was trying to set up. I might take a little trip to San Diego and didn't want to lug around a computer and a monitor. I just want to use my laptop from there.
That's it. Thanks. Take a look at Tailscale.
Thank you.
Yeah, I've set that up before, Ted, if you ever have questions on that for friends and stuff like that. So
yeah, I used to just take the computer with me, but it's a little effort.
I actually had a question for because the way I described about accessing the notebook through a web browser that's actually posted on another server is kind of a stitched together method. Has anyone used Jupyter Hub or those kind of server-based Jupyter so that you can actually run it, I think, the way Kaggle does and the way Colab does on a server?
So I manage a bunch of Jupyter Hub instances for the office. That's really about making it such that you're doing multi-user setups. It doesn't change a lot of the connectivity needs that are there.
So it doesn't publish a web page that you go to that you can then access and log in and then access your notebooks and run it locally on that server?
It doesn't really do it any different than, say, Jupyter, standalone Jupyter does. It just makes it such that when you do log in, you can have multiple people hitting the same thing. But when it comes to I need to connect to Jupyter Hub, it still needs to be exposed either, internally VPN or directly on the internet or whatnot. So it still has that factor to it. You're just basically replacing that Jupyter token with, you know, a user system.
Oh, so you still have to do the like reverse SSH tunnel for
Yeah,
Jupyter Hub as well?
you would, yeah, like however you're kind of securing your network layer, that part doesn't change because it's just another website like anything else. It doesn't do anything from the standpoint of publishing stuff in other, you know, in other mechanisms, right? So they look very similar from a network architecture standpoint.
So Chris, either Jupyter or Jupyter Hub would just be a browser on port 80443.
Yes.
And so if your home internet is dynamic IP, that's the hurdle you need to get past with a VPN or with one of these other services.
Yep. Yeah.
So if nothing else, we'll go on to chapter 10. So chapter 10 is a continuation. Again, it's kind of going through some of the nitty-gritty details of this specific data set. If you're trying to follow along directly with the example, you can dig in and you can see what every single function is doing. I would say if you're not trying to actually run the code, then I wouldn't worry about it too much. You can kind of boil it down and just get the distillation of the general idea of what they're trying to do. So in the previous chapter, they poked around at the data a little bit, and we see that there's two different files. There's the MHD files, which is the metadata, and there's the .raw files, which are the actual 3D arrays, the CT scans. The file names start with the unique identifier, and that's how you map those two together. So you have a UID for the MHD file and a UID for the raw file, and if they match, then you know that they're the files that correspond with each other. One of the things they noted is we've got this big data set. We probably want to reduce it in some way, but we want to reduce in such a way that we don't lose a bunch of signal. And so how exactly you do that is kind of tricky. You need to look at your data and you need to understand what of this is not that useful, what of this is actually what we want to use in order to make predictions, and what do we think is valuable for predictions. So that's just understanding your data for each specific project and saying, okay, this variable is useful, this variable is not useful, or maybe I can take this image and crop it in some way and reduce some resolution so I don't have to be dealing with as much. There's a lot of different things to consider there. And so in the second section, they're doing what I personally do all the time, which is we have this pile of data and I want to prepare it for a neural network. And the first step is just saying, how do I load this file once? How do I load the first file and the other first file and piece these all together? And how do I make an input and how do I make a label? So you just do that process once, just in your prototyping phase. You don't want to fully engineer the whole solution and then figure out when you get to the end, oh, these don't necessarily piece together exactly how I expected. So you want just a single sample to prove that you can at least load the data in a reasonable way. And then once you get that initial loading and the understanding of what the data is and how to piece it together, then you can start putting the whole data loader together where you're saying, okay, now I'm going to load all of the data, I'm going to organize everything properly. And so in the chapter, they're looking at the files in various different ways. They're using command line tools. If you're familiar with those, you can use those. What I typically do is I'll open up a Jupyter notebook and I'll say, okay, this is a CSV and this is an image, and I need to figure out how to open the .raw file with some special package and stuff like that. And so I'll just sit there and I'll say, what's in this file? What's in that file? What do I do in order to look at this data? And that's a pretty common process that you'll come across in most projects. And then after that, they're talking about, we have all of this data, how do we split it into train and validation? We probably want to set aside some data, so we'll train on this set of data and then we'll figure out how we'll perform on unseen data in some way. And there's a lot of different ways you can do that. So some people might say, let's just take the first 80% as training and the last 20% as validation. But there might be a lot of other considerations given your understanding of the data that might need to be addressed. So for example, if these are CT scans, and we know that a lot of these are repeat scans, so potentially some person gets checked up on multiple times, you don't probably want them on both your train set and your validation set, because just the fact that they occur multiple times might be a sign that they're more likely to have something wrong. And so you might be able to get good prediction by basically learning, when I see a person of this shape and the lung of this specific person, they know to predict tumor and stuff like that. So you have to split it in some significant way. And there's all kinds of different angles you can look from. So another way you might look at it is maybe there's some hospital that has a higher risk. This hospital is specifically for high-risk patients. And or you have some hospital that you don't have very many scans from. And so it turns out you put all of them in your validation set, and now you have no chance of ever getting them right because their scanner is a completely different resolution or something like that. So you really have to dig in there and figure out what is actually inside of this, and how do I correctly generalize for the situation that I'm looking for. Are you trying to generalize for new hospitals, or are you not? There's a lot of different things that could happen there. And one of the things they mention is there can be mismatches, there can be corruption, there can be all kinds of different stuff in data. I personally run across this a lot in my various things where you have the opportunity of, do I fix this issue that's 1 in 100,000, or do I just skip it and I just say, okay, we just won't use that sample for training. And that's something you have to consider. So in this case, if we only have 2,000 patients, for example, you might want to do that extra work to maintain things if you find that you're missing some data for some reason. But if you have, like in my case in the BAS project, over 100,000 samples and only 50 to 100 are wrong, then maybe you just say it's not worth my time to actually dig in and fix all of these data loading errors. So just something to keep in mind when you're doing various different projects. One of the other things they mentioned is writing a sort of debugging loop. So as you're building this whole pipeline, you don't want it configured that you only figure out that your validation loop is broken after you do a full pass through the training data. So you might want to do something where you say, you configure a branch of your code to say, only operate on 100 samples or something like that. So you can quickly say, okay, it can train correctly, it can validate correctly, it can save the model correctly, it can do whatever your process is. You want to have some sort of branch that just says, okay, I can actually run this without saying, every time I run this, it's going to take 24 hours just to figure out, oh, I misnamed this variable. That's a pretty valuable setup to configure for yourself whenever you're doing these projects and building them from scratch. So then in the third section with the CT scans, one of the things they mentioned is there's the DICOM and there's the various different file formats. Like I mentioned before, sometimes you might just say, I have no idea what a .mhd is. And so you have to go and you have to look, is there some Python package that will open an MHD? Is it really just a CSV with a different name? Is there some different way for me to look at this without me needing to write some custom code to decrypt this miscellaneous file? And so that's just something to keep in mind. You might get something in some bizarre format and you can just Google it and figure out, oh, it's this thing and there's a package to already open it, so I don't have to worry about it too much. And then they were talking about various different things. So if you have very high readings or very low readings, then that probably isn't that useful for this specific scenario. So they were saying if you have metal or if you have air, then it might give you some sort of reading that isn't really material to the actual body. So you want to filter those extreme values out. So they said basically they're going to clip it at -1,000 and 1,000, and then that's kind of the operating range where body densities actually occur, and so that's the range that they care about. So that's one example they're showing of like this, reducing the data down. They're reducing that data, and that's making it so the model can focus in on the stuff that's actually relevant. So just one of those tricks to keep in mind. So one of the things they were mentioning with these 3D images is you might have dimensions that are different on different axes. So on the height and width, it might be every voxel is, or every unit is 1/10 of a millimeter or something like that. But then on the depth axes, it might be something else. It might be 0.25 millimeters or something like that. So you have to keep that in mind and understand that maybe you want to resize that, maybe you don't care. But if you're trying to measure something, then you probably want to have that understanding of your data and make sure it's standardized in some way. And that's another thing where across scanners, you might have one that's this resolution across this axis and this resolution across another axis. And so when your model is looking at it on one scanner, it sees, oh, wow, this mass is very big. And then it looks at another scanner and says, oh, this mass is very small. But fundamentally, they were actually the same thing, but you were just using different units. So that's just part of understanding your data and making sure that it's a format that actually makes sense. So then in the final section, they were showing how to construct the data loader. They have all that code in there, but it really boils down to, we want something that can take in the index. So it's saying this is sample 0, this is sample 572, and then we want it to be able to output all of the stuff that we're interested in. And the stuff that we're interested in this case, is the 3D array that's been transformed in some way to make the units similar, and with the clipping and all of the other cleaning steps that they've created. And then we also want the label of, is this nodule or is this not the nodule? And then we also want the series UID, and that's useful for potentially several different reasons. It might be useful for logging and seeing which ones are we getting wrong, which ones are we getting right? Is there some specific scenario where we're getting them more incorrect? We need to focus on that more, and that will actually tell you which specific samples you should be troubleshooting on and looking for more accuracy from. And then the last thing was the center of the nodule. That was the, like, they were calling it index column row, but I think of it still as XYZ. And that's basically the center of the cancerous mass, in my understanding. And so you want all of those for the various different pieces of the pipeline that they're configuring. So those are the 4 things that are coming out of your data loader. And then with the train and validation set, they made it so that on the init, when you're actually creating the data set, you can define, is this a training set? Is this a validation set? Which samples do I specifically want in the 2 different sets? And that was basically where they finished the chapter and said, here's how you load the data. Here's a completed data loader. And now for the next chapter, we're ready to actually potentially look at what do we do with that output in order to train a model. So that was it for chapter 10. Does anyone have any questions to this point?
A quick comment. I got to the part of the chapter where they said, hey, in these 2 different files, the coordinates for the nodule or whatever, like have some slight different calculation / rounding errors, so they don't match. I was just like, oh, this is just way too annoyingly realistic. Like, I mean, right? I mean, that statistic you hear, right? 75–80% of time on projects is spent on understanding and cleaning and figuring out the data or whatever. And it's just like, it's very realistic. It's appropriate to teach people this, and oh man, that sucks. We have to do this even in a book.
One of the interesting things that I think a lot of these books leave out is sometimes you're actually the person collecting the data, and you have to figure out the formatting and how do we actually label this? So I think it's an interesting problem on its own to say, we've got 3D data, we've got doctors who are able to label it. How do we give them a system so that they can actually say, here's the bounding box around the nodule, here's the correct coordinate? I think it would be interesting to see how Project Luna actually did that, because I think that's also a valuable skill that's kind of undervalued.
Yeah, on that note, does anybody have experience with some of the sort of freemium image labeling services that have set up like SaaS services for that sort of stuff?
I haven't necessarily used any of them. I don't have experience with that. I know people who have used Mechanical Turk and various different things, but I haven't used any of the sort of specialized services for that.
One other question on this, maybe it gets into this in the book, or if other folks have experience here too, is the trade-off or sort of the amount of information that you're able to gather via that manual review, right? Like looking at the file formats and just noticing things with the human eye where the scales are different or something, versus more automated approaches to finding things that you should pay attention to in the data set before you start trying to train a model, right? Whether that's sort of unsupervised stuff like clustering or other like image segmentation models, right, that might help as a pre-processing step that you don't actually end up using in your eventual model, but that you use to get the lay of the data, basically.
There are platforms that accomplish basically creation of optimal training sets using your data set by doing that unsupervised learning to give it a nice diverse sample of data. And I imagine they have a lot of visualization and statistics to help you do that.
Regarding your first, sorry, go ahead. I didn't know you were.
No, you go. You.
Oh yeah. Regarding your first thing about those services, I have a friend that tried using Scale AI's image segmentation service, and he wasn't really a fan. I think the quality wasn't that great in terms of whatever algorithms they're using. Like they honestly had to scrap everything they gave and hand label a good bit of it and then work on it on their own. I didn't really follow up too much, but they didn't have that much luck with that. But on another end, I was just helping some people like learn how it works, and they have like a free little trial with Scale. So I try to like have them go through a unique project that they probably wouldn't have seen before. So we just got our own data and had them label it with the labels that the students would create themselves. And it was good enough in like a learning sense, but in the production environment, they didn't find it to be adequate, even though that's what it's really suited for. So that's the only experience I've heard of it.
So if I'm understanding correctly, almost using it as a prototype of a labeling system, just for people getting the sense of what image labeling is.
That's just the route that we took, just because I was the first one that I'd heard of, and they did a decent job. But I think a lot of businesses do actually use their services, and it's quality enough for them. It's just that the person that I tried it didn't have the same experience, but I'm pretty sure that they're supposed to be pretty good, like for actual production setting.
So if I'm understanding part of the second question properly, you were kind of asking, so in this data set, they figured out, oh, maybe we need to clip the upper and lower values, and maybe there's certain files that aren't going to be loaded in properly and stuff like that. I think what you were poking at is there's some automated way to figure out what characteristics of the data might be interesting to look at automatically and figure out what decisions need to be made. Is that kind of what you were asking about?
Yeah, that's part of it. And the other part is, given that there are tools out there that do this sort of thing, do folks have experience in that trade-off, right? Like, is it 80-20 where you get 80% of your insight via the human eyes and then 20 is the machine, right? I'm sort of looking for anecdotes and insight into that trade-off. I've got a project where I'm trying to figure out which way to stab at it first.
Mm-hmm. I've never personally used tools for that. I've typically just had the best luck just manually looking at it. And I know a lot of people, like I've seen stuff on Kaggle where they'll say, I'm going to plot the distribution of the size of the images and a lot of different factors. And you can kind of visualize it and see, okay, here's the various different things that are interesting. Why do I have a whole bunch of images that have a resolution of 4 by 4 pixels or something like that? So that's the stuff I've typically seen. I've mostly seen people use the manual approach. I don't really have any experience with tooling related to that.
I might add, I see Hobson has a note in the chat that he's looking for this service that he heard of. I think you could automate things like identifying features that don't have any useful information, like say it's 99.5% zeros, and so there's just not a lot of information variety, and looking for collinear features and things like that. I feel like that could be done in a fairly automated fashion, could be kind of useful. I'll say that if ultimately you need to do feature engineering, which we don't really talk about in this PyTorch book, we're not really going to. I think the author said they're not really going to talk about it for the CT problem because they're really focused on building the neural networks. Then I think you have to do that EDA. Even if the automated system got it right, you still don't know your data now, So that's just like my little side comment is that if you're going to need to do that, then you're going to wind up having to manually explore and look at it yourself anyway.
Yeah, thanks, everyone. Great insight.
Ryan, did you have anything else you wanted to share? Other weeks, it was more code heavy, but I don't know that there's much, the code's too interesting for chapter 10. Yeah.
In the past, I've shown the notebooks. In this one, I'm not sure what we're going to do moving forward because I'm not necessarily following along with it at this point because I don't have the extra compute bandwidth to do the whole project. I do have a computer that can handle it, but it's working on the lift competition, so I don't have excess cycles to run all of these examples necessarily. In the future, if anyone is trying to follow along and they want me to specifically explain anything, they can point it out and we can dig through it together. But I'm thinking in the future, maybe we don't dig into the code as deeply since we don't have people necessarily directly operating with it.
Yeah, I haven't done it, but I was thinking of I should be able to get it loaded on my laptop. So I don't know if I'll actually run it for like the full number of epochs, but at least that way it's working in case somebody does have a question about what some little snippet in the code does.
Yeah.
All right, any other questions? Well, we like to do breakouts, but since it's 5 till, I don't know, is 5 minutes enough to do a quick mini breakout? Any thoughts, votes?
I think that's kind of too short. I think maybe we take a long lunch.
Longer for us, 20 minutes, what a luxury.
Yeah.
All right, well, thanks for joining us, everyone. So we'll be continuing with this part 2 for the other Saturdays in October. So we're gonna do the classifier, which is actually kind of jumping to the end of the pipeline next. And then the book goes back and deals with segmentation, and then it connects everything together end to end. And so that'll be the next 4 Saturdays. So chapters 11, 12, 13, 14. And then the book only has one more chapter after that, Ryan. Chapter 15 is a deployment chapter. All right. So I would encourage if you're not on our Slack, you can post questions there, and also we just generally have announcements both about Meetup itself and as well as general ML type stuff. And so I've already posted next Saturday's Meetup, the 10th, on Meetup if you use Meetup. Otherwise, basically, same bat time, same bat channel. We'll see you next week.
Thanks, guys.
Thank you.
Thanks, everyone.
So for everyone who's new, just for everyone's information, what we typically do here is we take 15 minutes break, and then whoever wants to can stick around, and we just talk about the various projects we're working on. For me, I've been working on a competition on Kaggle, so I'll share a little bit about that. If anyone else has anything they're working on at work or just as a side project or doing a competition or having a struggle on something technical, feel free to come back in 15 minutes, 30 minutes, or whenever you're available, and you can come and talk to us and just hang out.
I did have a question, since this is a PyTorch book, if anyone else has tried the tracks framework. So I know most people use TensorFlow or PyTorch, if anyone's worked with tracks. I spent my last week and a half doing that NLP course. I had finished it before, and then they added course 4 last week, and I spent so much time just trying, because they switched over to doing it in tracks, which is another framework for machine learning. Oh my God, I hate it. But I just finished it yesterday, but it was such a mess. If anyone's gone through that, I don't know how you work with that.
No, I haven't, but I was
great,
looking at the NLP track, and so yeah, you had mentioned an earlier week, and so I had my eye. I was really looking to see, and I was like, oh yeah, they really are using tracks.
Oh, they use it so much, but the content was actually really good. A lot of what I ended up doing was just the videos were pretty decent, but I'd end up just looking more into every topic myself. But when it came to the actual assignments, oh my God, it was such a mess.
There's a question.
All right, everyone. I'm going to leave the Zoom open, but usually what I do is I just turn off my video and grab a quick bite. So it's 1:59 right now. So in 16 minutes at 2:15 Pacific, we're going to come back together and talk about Kaggle projects and whatnot. So those of you who want to stay, we'll see you in 15 minutes. Thanks.
Thanks. Gotta head out. Take care.
mild cough and fatigue are improving, but the Associated Press reports that White House Chief of Staff Mark Meadows says the president went through what he calls a very concerning period on Friday. He says the next 48 hours would be critical in terms of his care. The Senate is delaying its return to full chamber business by 2 weeks. NPR's Claudia Grisales reports that Majority Leader Mitch McConnell announced the news after at least 3 Republican senators said they had tested positive for the coronavirus. McConnell said he'll return to the chamber on Monday to seek a consent agreement to allow the Senate to resume floor business on October 19th. The move comes in the wake of reports that several Republican senators, including members of the Judiciary Committee, have tested positive for the coronavirus. McConnell says the Judiciary Committee may still proceed with its plan to hold a confirmation hearing for President Trump's nominee for the newest justice on the Supreme Court, Amy Coney Barrett. Then the full Senate can pick up the effort later this month, potentially in time to approve Barrett to the court before Election Day. Claudia Grisales, NPR News, Washington. In South Carolina tonight, Republican Senator Lindsey Graham and Democratic challengers from Harrison will meet on the debate stage for the first time at Allen University, a historically black school in Columbia. As Gavin Jackson of South Carolina Public Radio reports, the debate comes a month before voters determine whether Graham takes a fourth term.
Heading into tonight's debate, both have Graham and Harrison, the Associate Chairman of the Democratic National Committee, deadlocked. Top forecasters have moved the race to leans Republican, which still favors Graham in the Republican-controlled state. But changing demographics and Graham's shifting views have fueled his nationally connected opponent to smash fundraising and ad spending records. The confirmation process of Judge Amy Coney Barrett and Graham's Judiciary Committee threatens the next 2 debate dates. But it can also boost campaign confidence, something Graham desperately needs. For NPR News, I'm Gavin Jackson in Charleston.
And you're listening to NPR News. Today's NFL matchup between the New England Patriots and the Super Bowl champ, the Kansas City Chiefs, have been postponed in the wake of multiple positive coronavirus tests. As NPR's Javon Paris reports, the second game scheduled for this weekend still won't happen because of the virus.
The NFL says the game, originally scheduled for Sunday, will take place later in the week. In the statement, the league says, quote, all decisions will be made with the health and safety of players, team, and game day personnel as our primary consideration. Patriots starting quarterback Cam Newton, as well as Chiefs practice squad quarterback Jordan Ta'amu, have both tested positive for COVID-19 and have been placed on the league's reserve COVID list. Both will be eligible to return when they are declared healthy. The other game postponed this week was the matchup between the Tennessee Titans and the Pittsburgh Steelers. That game is being moved to the 25th, following several positive tests within the Titans organization. Javon Paris, NPR News.
The chief executives of Facebook, Google, and Twitter all agreed to testify before Congress at the end of the month. This about a legal shield that protects the tech industry. This comes shortly after the Senate Commerce Committee of tech company CEOs to talk about a decades-old protection that lets tech platforms avoid getting sued for what people post. It also lets the companies moderate the content. Democrats say that law has let misinformation and hate speech spread. Republicans says it has silenced conservative views. I'm Jeanine Hurst, NPR News.
Support for NPR comes from NPR stations. Other contributors include Elijah Craig, maker of small batch Kentucky straight bourbon whiskey, aged and bottled in Bar 47% alcohol by volume. Elijah Craig promotes responsible drinking. I love to play games there instead of. For a long time, I was afraid to admit how much I like playing games because it seems a bit childish. And as adults, we are encouraged to do away with childishness. But you know what? I've changed my mind because playing games means that you're taking part in glorious professional.
Isn't the world a remarkable place? I love looking out at the horizon and imagining all of the possibilities. You never know what's going to happen until you begin. Hey, ready? We're going to get in so much trouble. Every day for school. Understood. And don't burn down the house. Double understood. I want Green Gable standing when I come back to the yard. I believe there's always a bit of good in any situation, even a bad one. It builds character.
My face is as a family. The three of us.
There's nothing wrong if you're different. You're unique.
Unique means weird.
I think it means singular and extraordinary.
There are more important things than beauty. Please try to remember what's real and good. What could be better?
Now I remember that the real world was born in the varied field of hopes and fears, of sensations and excitements, awaited those who have the courage to go forth into its expanse. Have you ever heard anything more than it?
That's Martin Walker. We recorded him a while back, pre-COVID, at a board game cafe in Greenwich Village, New York City, called The Uncommon. He was with his wife, Jenny Chin, and a friend. They were playing a game called Takenaka. It is a map-building, bamboo-growing, panda-eating board game.
It's not really a group work thing. We're
each helping to grow a farm, but we're also taking advantage of what they built and taking it from them.
It's kind of similar to Settlers of Catan. Yeah, you're building the same map, but you have your own agenda. Yeah.
Greg May is the founder of The Uncommons.
I've always loved board games, and I've always felt like there needed to be a place, a sort of home for games in New York City.
So that's what he started, with a collection of nearly 1,000 board games.
Catalog to a bit, Netrunners, Five Tribes, classics like Operation, Mousetrap, Heroes of Normandy, or Merchants of Venus, almost a dozen different versions of Dominion, Star Wars, Lord of the Rings, Walking Dead. We have games with filters, like Filch Show, trivia games like This Is a Wager, and games like Pandemic. There's been this explosion and growth in games that weren't around when I was a kid. I've just already Bad Medicine, which is a party game where the players are all pharmaceutical companies making horrible drugs.
That's Neil Hova. He's a board game designer and publisher who lives in Jersey City.
I usually drop by here just to see how things are going, what people are playing, what's been selling, that sort of thing. I have a game called The Networks, where the players are all running television networks, starting with 3 horrible public access shows, and slowly improving your network over 5 seasons. The business has been incredible. I raised over $100,000 on Kickstarter for The Networks.
That is a true fact. And Hova is not the only game designer crowdfunding his work. Kickstarter has an entire division dedicated to games. Since 2009, about $1.3 billion has been pledged to games. A lot of these are video games, not old-fashioned board games. And before you get too excited about some board game renaissance, consider the sales numbers on board games versus video games. Board game and puzzle sales in the United States bring in about $2 billion a year. Video game sales total $35 billion. So for every dollar we spend on board games and puzzles, we spend $18 on video games. Play some
Hobson, can you please mute yourself? Because I hear, for example, how you type.
Oops, sorry.
It's fine.